One of the objectives of this section is to identify strong assets, and Table 9.1 of your textbook lists the 6 strong assets that you will be responsible for. And what makes an asset strong is that it completely dissociates in water. So the 6 strong assets are perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. And the little asterisk here symbolizes that only the first proton in sulfuric acid is 100% dissociated. So remember, when we use the term dissociation, it means that the species breaks apart into ions. So on this slide we have the dissociation equations for these 6 acids. Now I just have the dissociation into the proton because I think it's just easier to see how it dissociates. So hydrochloric acid dissociates to a proton and chloride, hydrobromic acid, proton and bromide, etc. And then down here for sulfuric acid, a proton and bisulfate or hydrogen sulfate. Now notice that the arrow only goes one way, so that means this dissociation is complete and none of the molecule where the hydrogen is connected to the anion exists in solution. Now I just want to point out I use the proton here just for convenience when we look at the dissociation, but a proton is very reactive, and anytime a proton is in water, it is going to attach itself to a water molecule and form hydronium. Now, weak acids will be any other acid that is not on that list, and weak acids only partially dissociate. So that means only about 5% of the molecules actually break apart into the ions. Sometimes this dissociation is referred to as ionization because ions form. So an example of a weak acid is acetic acid, which is the main component of vinegar. We know it has a characteristic taste and smell. So acetic acid is a carboxylic acid. When we see this Cu in a formula, we know that that signifies a carboxylic acid. When acetic acid dissolves in water, it donates a proton or loses a proton, and water accepts that proton. So on the right hand side of this equation we see acetate, which is acetic acid that has lost a proton, and hydronium, which is water that has gained a proton. One thing I want to point out is that hydrogen that is bonded to carbon is never acidic. Those are very, very strong covalent bonds, and for a hydrogen to act as a proton, to dissociate, it has to be bonded to an electronegative atom such as oxygen. Another thing I want to point out is there are these double arrows, which we may remember means reversible, and that means that this acetate and hydronium, when they come in contact with one another, are going to go back the reverse reaction and form water and acetic acid. So this graphic here shows you the difference between a strong acid that is completely dissociated and a weak acid that is only partially dissociated. So we have hydrochloric acid, which is strong, and acetic acid, which is weak. Now they both have the same concentration. There's 1 mole of hydrochloric acid per liter and 1 mole of acetic acid per liter. Their concentration is exactly the same, but the amount of dissociated proton is different. In HCl or hydrochloric acid, since it is a strong acid, there is 1 mole per liter of hydronium because the hydronium completely dissociates. And remember that whenever we see that proton, it is the same as hydronium because that proton is going to attach itself to a water molecule. Now if we look at the acetic acid and look at this little graphic here, most of the acetic acid is in the molecular form, where that acidic proton is still covalently bonded to the oxygen. There are a few acetate ions and hydronium ions, so a little bit of ions that form from the dissociation of acetic acid, but most of the solutes are undissociated acids, and by undissociated we mean that proton is still bonded to the oxygen in the carboxylic acid. So in a weak acid, it is mostly the molecular form of the acid and very little of the ions exist in solution.